find in bike time, and in Berkeley it's walk time.
Yeah.
So therefore you get 10 minutes.
Yeah.
That is the...
But yeah, Stanford is hopeless. It's too big.
Yeah, people, it's always... now the sensible thing would be that you end classes 5 minutes early and you begin classes 5 minutes late. So that way you have...
yeah, that's what the Illinois do. Illinois, we stop the class 10 minutes early. So then it starts at the sharp at the clock. So anyway, everybody has a different protocol to adapt to the. Okay. Good.
Let me start.
Yeah.
Okay. Hello, ladies and gentlemen. Welcome to the ECS Colloquium. I'm Jitendra Malik. I'm here to introduce our distinguished speaker today, Professor Yi Ma. I have known Yi Ma for a very long time, at least 30 years, maybe longer. So Yi got his undergraduate degree at Tsinghua, then he came to Berkeley, where he did his master's and his PhD. He was advised by Shankar Shastri, but I also served on his thesis committee, and we worked together. So what, in my view, the characteristic of Yi is that he is very broad-ranging in sort of the space of systems, machine learning, computer vision, control theory, today's AI. I think all the different facets of today's AI, he has worked on all of these. So let me give a little sort of journey here. So yeah, he started in control theory, and then he drifted to computer vision, and then he drifted into machine learning with various other side branches. So in terms of his career, after he finished his PhD at Berkeley, he went on to UIUC, where he was a professor, and then he went on to China.
Microsoft Research Asia.
Where he was, in fact, the boss of Microsoft Research, which is a very key organization in China, because if you see the tech industry in China that has taken off in the last 10, 20 years, many of the key leaders, they got their start at Microsoft Research Asia. Then after that, he was in Shanghai.
ShanghaiTech.
The dean there, I remember we had a collaboration between Berkeley and ShanghaiTech. And then he came back to Berkeley, and then he has gone back to University of Hong Kong. So he has paid his dues to the administrative gods. But while paying those dues, he has always kept some of his time for research and pursuing the good fight. And I've always enjoyed talking to Yi and listening to Yi. So without further ado, Yi Ma.
Yeah, thanks a lot.
That's
appreciate it. Thanks a lot. As Jitendra said, right? I don't know. I mean, kind of now looking back, my career is kind of eccentric, but nevertheless, I'm kind of going back and forth the two sides of the ocean, and also two sides of the aisle of industry and academia, back and forth, and also probably determined by the nature of the question we're looking. You know, I'm really interested in. Although I trained as a control theorist, but I'm really interested in robotics and also computer vision, right? And which is actually has very strong practical side of it. So we cannot, I'm really interested in theory. Today we'll talk a lot about it, mathematical principles, but also that what I think the good mathematical principle that can really guide practice, right? So that's actually we're going back and forth. We draw inspiration from the practice and inspire many of the theoretical problems I'm interested, as well as my theoretical training really helped me to probably find better solutions to them. So I think that's a very beneficial journey. Today I will talk a little bit about a subject probably everybody kind of fascinated about intelligence, right? And this actually has been the work. This is kind of journey I sort of embarked on since I came back to Berkeley, right? Before that I was in ShanghaiTech. I was, so a lot of, administrative duties distracted me from doing the research. But everybody know that it's about 2017, 2013, I left Microsoft Research Asia. At that time, of course, we know that after that, there's all this, deep networks start to, kind of dominate the practice, side, right? Including, my former colleague, Sun Jian and Kai Ming. Actually, Kai Ming was my first recruit when I joined the Microsoft Research Area. Then there's a lot of practical practice about deep learning has tremendous technological success, but there's not much understanding. And of course, let people also become the artificial intelligence or intelligence get back to people's radar in the past decade because of the success of deep representations. Since I come back to Berkeley, I finally got a break from my duty. I started to, give myself a little bit task. Can we understand things a little bit better, right? And hence, today's talk is kind of overview of what we did. I think even early on, probably even Venkat, right? Early on, when I first joined Berkeley, we started to become really curious what the deep network is doing. Can we provide some principled explanation and about it, to it, right? Then maybe go from there, try to understand intelligence a little bit more, right? So just like everybody else, in 2018, I joined Berkeley. Just like everybody else at the time, the theoreticians are very curious. There's a bunch of curious phenomena, right? The practice deep networks, generating a lot of practical observations, phenomena. It's very hard to explain, right? Or if you do this trick, that you get 5% better, right? Drop out. If you don't do it, you're not state of art. Or this normalization comes around. Then people start to writing hundreds of papers. Theoretician, including myself, by the way, right? Or if the thresholding, or there's the ReduNet is better than sigmoid, why? Or there's a double descending phenomena, and then we write another 100 papers, few hundred papers to explain why it matters, why it's interesting, right? And then, of course, there's a residual network comes around. Again, people start to analyze and, oh, this is great. This is actually end of the world, right? This is, if you don't do this, you're behind, okay? And again, I'm also guilty to write a few papers to explain why the world should be better. Around the 2019, my group students should remember, right? I put a very hard stop on my student. I said, let's stop. We cannot write papers like this, okay? Stop writing papers like this. I'm not going to put my names on papers like this anymore, right? Can we, because we're just chasing the tails of practitioners, right? Every 3 months, there's another trick. There's something else they tried. Seems to work better, okay? And it's just, kind of detrimental, right, for me. And, I said to them, can we really go back to the drawing board thinking about what the heck we're doing, right? For a long time, we studied deep networks as the object of study, right? Maybe, the time we ask, maybe it's a means to the end. Maybe something else is missing. And let's ask something a little bit annoying questions. What do we try to learn? Everybody says, machine learning. Machine learning, why? Why do we learn? What we're trying to do there, right? Or everybody talk about the word intelligence. What is the purpose of intelligence, right? If we can clarify the purpose a little bit, maybe, right? A lot of the things that the deep networks are just the manifestation of the means to the end. They're trying to do the same thing, despite all the difference, right? Only can we clarify the purpose, objective. We have a chance to be able to, to study how to learn. Then we can ask the question, are we doing the right way, right? Have we learned correctly, right? Those questions become meaningful, right? Hence, this is the little bit journey we're trying to do. And you can also summarize, in the past 10 years, we have done a lot of, the dominant methodology is inductive, is trial and error, is empirical, right? Now, maybe it's time to do a little bit of deductive thinking, right? At least make an attempt to do that, right? And again, I like the quote, right, from Richard Feynman. In order to understand something, we really probably have to create from first principle, clarify our simplest assumption, and then try our best to deduce everything, to explain everything. Then, hopefully, we can do better. So, through the journey, if you look at the world, right, there are probably two problems, the two most important problems to understand. One is where the universe comes from, right? That's the subject of physics, right? The laws of physics to explain our physical world, how it evolved, how it was born, and where it comes from, where it's going, right? And now if you examine, if you try to make an analogy, right, the intelligence is pretty much trying to understand life. is the mechanism behind life. I love this quote. Right? This actually very much carries on throughout the whole talk. Right? Just as the constant increase of entropy is the basic law of the universe, so it is the basic law of life to be ever more highly structured and struggle against entropy. And this actually captures very much the essence of everything we're going to talk about today, right? So in a sense, it's inevitable. The universe the entropy is increasing, but nevertheless, life finds a way to survive in this ever more chaotic world, right? To find something predictable, something not entirely random, right? So you can see the beginning of the life about 40 billion years ago, right? DNA, life matter start to appear. But you can actually, roughly speaking, you can actually think about that the DNA is actually our nature's first large models. Right? It encodes every knowledge that species has learned about the world, and also pass it on to its next generation. Right? And in fact, even the way the DNA evolved is very similar to today's big models. Right? Randomly mutate. Nature gets the latest fittest to survive. It's reinforced learning. Nature's ways to do reinforced learning. Of course, today's large model, the benchmarks, right? Selected by engineers at OpenAI or Gemini, okay? Made the fittest survive. Now, about 500 million years ago, something remarkable happened. Right? There's the emergence of brain and eyes. I actually learned that from Jitendra's right, lectures about vision. Right? That's a landmark event, because after that, this allows individuals to learn knowledge besides what they inherited from the parents. They no longer operate based on their pure instinct. Okay? They can develop the memory around their surrounding environment so they can survive better. Shortly after that, after 50 million years, that's a very, very short time in the life, right? You see the explosion of life, the Cambrian period, right? So this actually today has those two phases has two names, right? One is called the phylogenetic intelligence, which is really the species has intelligence to evolve under natural selection. Individual does not. Okay, they just inherit whatever the parents gave to them, then they react with reactive way, just like today's big models. And ontogenetic intelligence is really saying the individual life has the ability to learn, develop its own memory, right? Through perception, through feedback, and through error correction, right? Develop its own memory about the world, right? It's called ontogenetic intelligence. Of course, today has a very fancy name called embodied AI, right? Embodied intelligence, right? So life actually depends, intelligence actually depends on the fact that the world is actually not entirely unpredictable, right? To learn what's useful for their survival. Now, later on, we try to attempt to give a definition of what the intelligence really is, right? But now let's use our common sense, which has become a rare thing in the past decade, by the way, right? Before you say, we all agree, right? For more primitive lives, the intelligence is lower, right? More advanced life form, the intelligence is higher, right? No matter how we measure it. You can see something very interesting, right? The more advanced form of life, they stay longer with their parents after birth. You ask yourself, why is that? Right? You're more advanced, you're more superior. Why you stay? My two kids still with me. One of them is 18 years old, right? I cannot wait to kick them out, right? It's too long, man, right? And why is that? Which suggests that we depend less and less on our pre-trained models. The ability to adapt, to learn, acquire your own knowledge is crucial for your survival, for your success. Now, after that, right, about 1,000 years ago, 10,000 years ago or more, right? And humans start to emerge, right? Human society. What distinguishes human society from animals? We believe by language, where we start to be able to communicate with each other, and also written language. We're able to written down our knowledge, pass on to the next generation. The spoken language allow us to talk to each other, share my useful information with you, right? So that actually, if you think about it, this actually collectively improved individuals' efficiency of acquiring new knowledge. I can tell you where the danger is, where the food is. So you don't have to risk or spend the resource to learn that piece, right? So that makes us societal animals, right? That's how civilization gets built. if you think about even the natural language is kind of took over a little bit of the role of DNA. We're able to read down our knowledge learning this generation, pass on to the next generation. So they don't have to spend the resource to relearn it, right? And about 3,000 years ago, something remarkable happened, right? That took a lot. You can see up to this point, a lot of this knowledge will accumulate still through empirical ways, right? But about 3,000 years ago, a bunch of philosophers and the Greek philosophers started to develop something very interesting. They started to develop abstractions, concept, mathematical concept, logic, causal inference, geometry, right? That becomes the new language, code book for different type of knowledge. Science was built on it, right? And it changed how we develop information. So you can see after this, our developing of the unknowns become proactive. Before that, it's kind of, reactive, right? We learn from experience, try and error, mistakes. But after this, we start to formulate the hypotheses, conjectures, and through deductive means, through experiments, to verify that. That, again, tremendously improves the efficiency, how we learn unknowns. And around the 1940s, for obvious reasons, right? Everybody can guess what the reason is, that people start to be interested in to have machines to emulate the kind of intelligence that animals or humans have, right? So everybody these days, whenever they talk about artificial intelligence, think 1956. That's actually an embarrassing way, okay? I mean, you guys should know better, right? So the true origin of intelligence, stars, that's a true magical era, is not the 1950s, right? It's 1940s. People start to try to make a machine to imitate intelligence, hence imitation game, okay? One name you should really remember is the Nobel winner, okay? This is the guy who started everything, right? Influenced everybody. By everybody, I mean everybody, okay? He's the first interested in trying to, where the animal intelligence come from? Can machine imitate something like that? Especially, he studied zoology as an undergraduate at Harvard, and then become a mathematician, developed control theory, systems theory, and so on. And he's actually curious. He has actually written a very famous book, Cybernetics, on control and communication in the animal and the machine. Okay, he's trying to have a machine to emulate the animal intelligence. Because he's interested in intelligence, but also he doesn't know where to start, right? But at least there is an existing solution in the world, right? That is our brain, right? He said, well, he encouraged his postdoc, Walter Pitts, and working with some psychologists to study how neuron works, that he developed the first artificial neuron models. And also he inspired his student, right, Claude Shannon. He's the first one said information is the third fundamental quantity besides energy and mass, okay? But he doesn't know how to measure it, but his student, Claude Shannon, developed information theory, tells us exactly how to measure information, knowledge. We'll talk about that later. And so also, because under his influence, that von Neumann actually is, you can read the historical roads. Von Neumann actually developed the architecture for modern computers, precisely try to develop a machine and carry out the kind of mechanism that he suggested for cybernetics. Okay? You can read their personal correspondence. And of course, in 1950, inspired by all this development, Turing started to ask this question, read a paper, famous paper in 1950, that can machine think, ask this question, right? Can machine think like human, basically, right? He started to say, what's differentiate human from animals, right? So hence the Turing test gets suggested, but he didn't give answer. But nevertheless, at least at this level, at the machine level, this period, people are really interested in this problem. We have an open world. We try to, through perception, eyes, senses, we try to develop some memory. Today, there's a very fancy name called the word model, okay? Memory, so that we can use the knowledge to predict what's going to happen, right? Next second, next days, next years, right? So it's really through this kind of closed-loop feedback to try to learn knowledge, useful knowledge, memorize it for future use. Of course, in the beginning, right, people know, well, we can model neurons inspired by some Nobel Prize-winning work. This is first artificial neuron models. This is like a human nature, right? Whenever we know a little bit about nature, we start to become very obnoxious. We thought we know everything, okay? So that's exactly what happened, right? People, after they know, oh, this is how neuron works. Let's try to build machines, right? This is a perceptron. Everybody know a little bit of history. 1950, U.S. military spent about $6 billion or something, which is kind of equivalent to $1 billion today, okay? This is about 500 nodes. They try to recognize digits. Sounds familiar? That recognize digits. So if you actually know a little bit of history, right? These days, students, we are all very anxious. What's going to happen in the future, right? But there's a lesson we learn in history, right? If you want to know the future, learn the history, right? History repeats itself, right? So if you read the newspaper of the time, almost everything we bragged about our artificial intelligence today has already been bragged then, okay? Oh, the machines start to think. I mean, the military is doing something secret. The machine can think for themselves now. They actually become conscious. Actually replace all the jobs in the world. We're just sit home, and they're going to do all the work for us, right? Nothing's new under the sun, right? Of course, it didn't work. Of course, still some people insisted. So this is the thing. People will never really become humble again until we hit the brick wall, okay? So after that, the people say, maybe there's something we don't know about the brain, right? There's still something new. They start to re-examine how the brain, the neurons gets arranged. They learn a little bit, a couple more tricks. They're actually structured, inspired some convolution neural networks. And that actually definitely works better, right? I mean, Jan LeCun was actually awarded because of that effort, right? He actually simulated in machines, actually those kind of networks works better in recognizing digits. Sounds familiar, right? And then actually, but now as a young students, everybody know this piece of history I know, right? Alex Glad, when people there's a lot, there's GPUs, there's more compute, there's more data, and suddenly we implemented the same old idea that actually seems to work better, right? Alex Glad, GoogleNet, VGG, ReduNet. I'm old enough, right, to go in the early stage and go through this kind of wild west, the evolution of deep networks, right? By artificial selections, okay? And those are just a few survivors, right? ReduNet, transformers. Anyone still remember roughly during this period? There's two very hot area, okay? Hot like crazy. Autolas, still remember? AutoML, right? You randomly permute the architecture, hope for something, you're lucky, right? You come up with some architecture, right? Right. Yeah, exactly. Anyway, there's very, very different effort, right? So, but turns out it's always through some heuristic trial and error, some of the network survived, right? And now, of course, later on, somehow people converge to transformer. But still, right? Well, it's actually an engineering marvel, right? I mean, this is a lot of effort, billions of dollars thrown at it, right? Computers and hundreds, thousands of people tried, and there's some lucky survivor. But of course, if you implement large enough, you do improve, just like nature, right? We have used that mechanism, evolved for 40 billion years, right? But extremely costly, extremely unpredictable, and even if you have done something, still a mystery. Right? We still don't understand the DNAs. But nevertheless, the outcome could be okay. It's still improve, right? Can understand natural language, image is better, and also, of course, even win the Nobel Prize, right? If you apply to the right problems. But there's still a black box. The problem is that, so there's still very deep networks, right? There's a lot of empirical part. Of course, there's a lot of people say I have all kinds of explanations, right? But not to the basically, to me, most of them, all of those explanations before does not meet the kind of standards we apply to other field, right? At least black box is difficult. The reason motivated us to study this is that the black boxes are difficult to explain, impossible to guarantee, costly to improve, at least. But around 2020, 21, 22, right? Our motivation changed a little bit, at least in my group. Before, it's out of curiosity, right? Just try to understand what the heck this thing is doing, right? But around 2002, the rhetorics in the society is changing. People start, especially after about the big models getting close, and people start to say crazy things, right? oh, the models start to become sentient, subconscious, right? And it's like a virus, and they're going to, wipe out the human kind, right? And now I think probably at that time, probably become more like obligations now as scientific community. I mean, scientists, we should have obligations to explain what the heck we have done, right? And then so that it's not up to arbitrary interpretations, okay? We have to provide the theoretical and experimental evidence so that our conclusion is trustworthy, rather than not some crazy CEO say things just to raise money for the next round, okay? To scare people. So again, can we ask the question, what do we want to learn? What intelligence is trying to do, right? Then talk about how to learn. And then maybe we can talk about have you done it correctly? Have you done it optimally? Or is there a way to make things better? What to learn? Well, so the point is that, see, yes, the world is getting more and more, the entropy is increasing, but yet the world is not, we are not there yet. We're not at the end yet, right? The world is actually not entirely random. It's still largely predictable. Now you ask yourself the question, actually intelligence and science actually learn what is predictable from sense data of external world. Well, in this sense, for this purpose, intelligence, even empirical one, and the science are actually doing the same thing, right? Hence, you can even argue, even every animal, cats, dogs, they are all Newton. They just don't know it. Why? Right? So everybody know, right? You don't have to know Newton's law. You know if I release my hand, what's going to happen, right? You already have a very precise model of gravity, how it works. The physical things work around you, right? Cats, dogs probably can predict that even better than you. Okay, if I throw the ball, they can precisely predict where that trajectory is. They have exactly the physical model, except they're written in different language. They're not written in differential equations, but it is equivalent in terms of purpose, in terms of even function, right? Now the next thing is that if we realize, what the way to maybe worth learning, what the purpose of learning is to learn something predictable. Now the question is, then can we formulate, at least attempt, right? Attempt to say mathematically, there is a unified way to formulate this problem, right? So what is the common mathematical problem behind trying to learn something predictable, right? It turns out, at least this is our first attempt, we can argue all predictable information actually is encoded as a distribution with very low dimensional support in a very high dimensional spaces, like our images. Look, like hundreds of thousands of pixels, right? Every image living is a point in a million dimensions, right? Million pixel, which means a point in million. But nevertheless, the distribution is extremely structured, right? For example, Newton's law tells us if a particle doesn't have any force on it, travels on a straight line. It's not going to jump randomly in a 3D world, right? It's restricted on the one-dimensional world. That makes things very predictable. Of course, the world is not as simple, right? There could be lies on multiple dimensions. There's still uncertainty. Or maybe multiple, or maybe they're nonlinear, right? That's slightly getting more general. But nevertheless, comparing to what's all possible, the only possible events are extremely low dimensional, extremely rare, okay? Make those things worth memorizing, worth learning. Now, I can argue, these days, also drive me crazy, early days, right? We studied deep networks. I have some argument with Benjo that not very pleasant. But he knows we have some workshop, and so whenever he sees some work worked, he said, oh, you must use the right inductive bias. Then something didn't work. He was, oh, you didn't use the right inductive bias. Then I asked him, what the heck is inductive bias, right? So then he sent me a paper, the 50 pages paper, and asked me to read it. And the whole paper doesn't have a single equation or definition. So it's just driving me a little bit crazy, right? It's purely qualitative, and I don't know how to use it, right, to explain if that's a convincing argument. What is it? So we can argue, right? So maybe assuming that the data you learn, the distribution is low dimensional, I argue that this is probably the only inductive bias you need. From now on, can we do deductive from here, right? So why low dimensionality is important? Well, It's very commonplace. For example, if we know Newton's law, everything travels on a straight line. If something gets occluded, we know exactly how to fill it, right? We complete it. Allow us to do completion. Now, if you apply the same rationale to just data in a high-dimensional space, text, sequence, or images, that's exactly the same thing, okay? Just apply to data in a very high-dimensional space rather than three-dimensional line in the three-dimensional spaces. Conceptually, it's exactly the same task, okay? Completion, low-dimensional structure allows you to complete. If you know your data lies on a straight line, of course, you observe something noisy. What do? You can denoise it, right? Clean it up, right? That's what we do. The signal processor has been doing this forever, right? Remember Norbert Wiener? What's his most famous work? Wiener filter. It's precisely doing this, okay? How to denoise your observation against low-dimensional linear models, right? A Kalman filter, everybody's doing the same. Also allows you to make your inference very robust, right? You know your solution should be satisfy certain equations, but you observe something completely violate Newton's law or Kepler's law. You must know, right? Your telescope is not clean, right? It needs to be cleaned again, right? There is something error wrong. So it allows you to do this. And you can apply that to higher dimensional data, right? Human faces. The distribution of human faces is extremely low dimensional. Some people argue 9-dimensional surfaces, right? Despite those points in the hundreds of thousands of dimensions, right? The intrinsic structure is very low. Hence, you can crop the images, randomly crop the pixels, 30, 50, 70%, right? And the machine, if you explore the low-dimensional structure, you can not only recognize who the person is, you can actually recover the image. Despite you know nothing, you don't need any pixel, you don't know which pixel is right or wrong, right? Here, you already cropped it beyond the wazoo, right? Probably your mom don't even recognize this. But the machine can, right? So this sounds magical, but it's actually very, very simple. It's exactly doing that thing, okay? Just in the higher dimensional spaces. Now, if we agree, right, if we somehow argue that the main object of learning is that to identify a distribution with low dimensional support and then transform them to some compact structure representation. This is argued. This is the definition of what we're really trying to learn, the purpose of learning. And we'll try to quantify this. Then, first question, if I know the distribution I'm pursuing is low dimensional, how do I pursue it? That's my only assumption, right? So you must, the only cue you have is that what you're seeking is low dimensional. Hence, the volume of the data distribution should be very small, right? What's the volume of a curve? 0, nearly 0, really 0, right? A point, 0, line, 0. Hence, you know the true data distribution has very small volume, right? And now you know, voila, now you start to realize, no wonder all the scientific laws, physical laws are written down equations. Have you ever asked yourself why they're all equations? Except one, the second law of thermodynamics, right? Is the inequality. You ask why? Because we learned from high school, right? If you have 5 variables, you want to solve equations, you need one equation, reduce the solution to 4. 2 equations, reduce the solution to 3, and so on and so forth, right? One more equation, reduce the dimension. Of course, partial differentiation reduce dimension even more dramatically, right? That's a different story. But nevertheless, equations reduce dimensions, right? Some people even argue, right? The whole universe lives in a 9-dimensional space, or 10, if you count the time, right? Now, nevertheless, but we're dealing with data that cannot, as beautiful, right? They cannot be written down by analytic form, okay? Images, for example, but we know they're low dimensional. There's some crazy red, blue curves in some gigantic spaces. Now, how do we pursue them? And how do we even measure them? So hence, this is a question, very, very bothered me a while, but later on I realized it. So imagine you are in the world, you're completely ignorant about the world. What would happen next day? Then the whole Greek world is possible. Then in order to record an event happen tomorrow, you need to code the whole space, right? But after you observe long enough, you realize only possible samples on the green and the blue and the red curves. You only need to, the volume is extremely small. Now, how do you measure that? Right? This is the notion of compression. If I only have to remember this, the volume of those red and blue curves is very, very small. Right? If I were to measure that, that small volume compared to the big volume, that difference can measure how much you know about the world, hence the gain of information. Right? Hence, compression allows you to know something from uncertain to more certain. So actually, Shannon actually gave an answer to how to do this, right? Entropy is precisely a way to measure the uncertainty or the volume, quote unquote, generalized notion of volume of your data distribution. That's it, right? It's just generalized. So why this is necessary? And we'll talk about this, right? Why entropy is needed and also needs to be fixed. Now, think about our problem, right? If we live in a world, we believe the world is according to some distribution, some low-dimensional structured distributions. Nevertheless, our observation could be noisy, right? Could be, adding a lot of noises to it. So we know if you have the ground truth, if you add noise to it, the entropy increases. The more noise you add to it, it becomes more diffused, right? Hence the diffusion process. Everyone knows this, right? Eventually become purely random. Okay, the world, that's what the universe is heading into, right? Eventually. But we're not there yet. But see, this is a boring process, right? This is kind of, just like, this is the same process if you submit one more paper to NIPS, right? We used to, in my days, we only have like 300, 200 papers, right? Now it's 3,000. How many of that is, it's a diffusion process, right? So we're not interested, this is not interesting. We're trying to reverse this, right? So we wanted to know what is the ground truth data is it? We want to denoise. We want to get rid of the noise, right? And this is the denoising process, right? If I have samples, we start from something unknown, guided by the data. We try to incrementally, through a denoising process, to gradually converge to the data distribution. Right? In this process, you actually can prove this following this so-called score function or the denoising process, empirical denoising operators, the entropy indeed decrease. You can rigorously prove this process. Let's do a thought experiment, right? If you're in a creature living in a one-dimensional world, right, and you observe after thousands of years, you say the value of this shows up with different frequencies, right? But if you're a believer, you believe your world, you're living in a world with some order, okay? And what you observe is some noisy. You want to discover that order, right? You see this histogram, right? So what do you think where the truth really is, right? If at this point, very naturally, right? Just use your common sense, right? This point, my observation might be noisy. Maybe this point gets corrupted from, more likely from the left, okay? This one more likely comes from right. So I should actually interpret it more closely to that. The same with those blue points, right? Move those points towards where more likely they have a higher chance to appear, right? Do this repeatedly, right? This is exactly the operator. You compute the gradient, right? This is a gradient pointing that direction. This point the direction point this direction. So you keep doing this. Gradually, you are reducing the entropy until you converge to delta function, right? Those are the only two possibilities. And you write down an equation which has two roots. You will be the Newton of that world, okay? You reduce one equation, reduce dimension by one, right? This is the only possibility. And then you can explain, right? So just apply exactly the same picture, just to a slightly higher dimension. Let's say a couple thousand, okay? A couple million dimension. Exactly the same mentality. Apply exactly the same operator, right? The same naive, right? Very incremental, right? If you do that, you'll see something seem to be meaningful to you now. The random noise converge to image that makes sense to you, right? Because those natural image has very low dimensional structures that are worth memorizing because it allows you to predict things, okay? And now you be the judge. Is this the virus? Is this the nuclear bomb? I can assure you, right? This is exactly Now the only thing, everything boiled down, right? So in one dimension, this looks easy, right? This problem looks easy, right? Here, I can compute the gradient, right? But if I'm in the million dimension, where the heck direction I should go, right? This gradient is very hard to find, all right? And also very hard to estimate. That's exactly how your tens of millions of GPU is doing, okay? You're paying, now you know what you're paying your money for, right? You need gazillions of samples to get a rough estimate, roughly which direction I should push my data to, okay? And of course, what is the form of that operator? I don't know. I mean, if you are bold, you just, let's try some deep networks. Let's try some transformers, right? It works, right? This is what voila, you get the you get the Sora, you get all the generative models, right? But the price is that you need a lot of samples to estimate that, to fit input-output, to estimate that gradient descent operators, that denoising operator, that's compression operators. Now, can we do better? Well, maybe we can, right? So if we make some assumption that's about this distribution, right? It's some crazy arbitrary surface in some extremely high dimensional space. But our learning tells us even you have very crazy surface, as long as the curvature is not crazy, we can always approximate that by piecewise linear models, right? Newton told us, all right, how to do calculus this way, right? We can approximate by pieces. Now, if we assume we can approximately generate low-dimensional distribution with a mixture of subspace or low-dimensional Gaussians, then, just like PCA, ICA, GPCA, sparse coding, then if you assume the distribution can be approximated this way, then you can write down what this operator looks like. Right? This is actually just calculus, right? Everybody should be able to do that. So this looks like this, but this, anyone play with transformer? This looks familiar. This is a tension head, right? It's a quadratic, two linear operators, another linear operators, do a soft thresholding, and and this is not the end of the story. The problem is not that, actually, this problem that troubles me for about 20 years, for a long time. There are other reasons. Now, we keep saying that our data is from some low-dimensional structure, right? Low-dimensional manifold, or let's say a straight line. But where we start actually, I'm not giving you the line, right? Where the line come from? I only give you the points, right? You only see those points. Now, if you argue, if our purpose to find the most parsimonious interpretation to compress volume, then actually we get the wrong answer, right? If you measure by volume, dimension, well, you would prefer the points than the line, right? Line has one dimension. Points 0 dimension. Our volume, well, both lines and points are 0. Which one should I choose? Entropy also doesn't cut it, right? Differential entropy, especially for distribution, continuous distribution with continuous support, with diminishing report, differential entropy is negative infinity. How do you compare between two are both negative infinity, right? So, and also, how do you differentiate these two? Why? Right, they're all 8 points. Each one shows up once, 1/8. What your criteria? How do you measure? Right? There are troubles. How do you measure? If you say you prefer one model against another, that one must be better in some things. Can you measure it? How do you measure that goodness? Right? Which one is more informative? Right? Then you apply this. So, for example, you actually do an experiment. You can do diffusion, right? You can start with very high dimensional space, converge to your data. Those data points will guide your denoising towards. But if you use a very powerful network, few number of samples, you end up with memorizing every samples. The individual samples will be the preferred solutions. You end up with memorizing. You don't converge to the straight line. However, when you have enough samples, sample gets dense enough, or your network capacity is limited, it will actually prefer the line versus the points. Why is that? It turns out you need a different. This is actually a question actually Shannon must have thought about, okay? The principle is universal. When we try to interpret anything, we always try to strike a balance between parsimony and subject to accuracy, okay? For example, even you have a simple world with 2 points. Let's say E, the natural number, right? E and then pi, 2 irrational numbers, right? computability and the memory is actually a thing, right? You say, if this 2 point, you're living in a world with only the 2 point, E and pi, right? Each one has equal probability. What's entropy? 1 bit, right? So in order to encode the 2 points, you need 1 bit. Okay, easy. But what about the decoder? How do you decode it? You need infinite memory, okay? It's useless. So that whatever you try to explain the world, you can only explain up to certain accuracy. So you have to construct a codebook with a finite memory, complexity, you measure it, and can explain your data up to certain prescribed accuracy. This is the notion of redistortion, right? How do you develop a best codebook to explain your data up to certain precision? And then everything become computable, Otherwise, you just talk about things in abstract, right? So hence, you really have to develop very clever lossy encoding decoding schemes. Find a codebook, right? For example, if you have data lies on those 2 lines, one way, if you're ignorant, I don't know the world, I can code the whole space with the blue balls, cover the whole blue balls, right? That's a codebook. Any point will show up, can fall in one of the balls. I can explain it, which ball shows up, right? Or if you live long enough, you realize only the green balls gets hit most of the time. You can throw away all the green balls. You don't have to label all the green balls. You get a much more compact codebook, right? Hence, you gain knowledge about the world, from ignorance to knowledge. Hence, the difference of the size of the codebook, or coding rate, or coding length, become a measure how much you know about the distribution, where it is, okay? So you actually start to be able to measure that, right? You can measure the whole space. You pack the entire space with some redundant codebook, versus you actually be able to, strategically find a codebook, a structure that fits the data just fine, okay? The difference, measure the information gain. The difference is exactly how much you reduce the coding rate, right? Coding rate and so on. Now, hence, this process to find it is precise through compression, through denoising, through dimensionality reduction, okay? The operator, we saw that before. Now, this is probably not the end of the world, right? So this only allows you to find what the raw data lies on, but it's not necessarily good representation. Why? Right? There's still correlation in the data, right? And things still get confused a little bit, right? May still confuse apple and oranges, right? If I can reorganize, spend a little bit of effort to reorganize, transform the distribution to have those 2 low-dimensional structures to become linearized or orthogonal, independent. This is a much better memory, okay? They become less likely to be entangled with each other. So hence, you can see intuitively, right? The ratio of the big ball and the green balls gets larger. Let's say, even you normalize both volume to 1, right? This shape, the ratio, will get larger. Hence, in order to get a better representation, the better representation maximizes the information gain for you, okay? It will automatically organize the distribution in your hidden space. So, of course, you can say that, we don't know, right? Those are, what are the distribution like this, right? Or even the overall distributions like that. We can start with something. By the way, computing rate distortion for arbitrary distribution is actually an NP-hard problem. It's incomputable. But we are lucky. For certain popular distribution, for Gaussians, we can, right? If we approximate, for example, if we think the desired distribution, final distribution, the overall is a Gaussian, that's exactly what variational autoencoding is trying to do, okay? A lot of regulation, SIG-reg is also trying to do the same. Make sure the overall distribution of the data features more like a Gaussian. And also for the parts, again, I wanted them to be linear. I want them to be more like each one more like a Gaussian, right? Then I can measure the volume very, very well, okay? I can measure the rate distortion very well. Those are given by those 2 formulas. You don't have to derive them. Actually, the people already derived for you. For Gaussians, those two formulas give you what the whole blue space looks like, the volume, and those are the pieces. If you have k pieces, each piece is this volume. The difference gave you the information gain or reduction of coding rate, right? Hence, remember, we try to learn a representation, maximize this quantity, right? It looks a little bit crazy, right? For students, this is some kind of nonlinear log-determined multivariable. We don't know how to optimize it. what even the optimal solution looks like, right? At least from a practical point of view, we can do gradient descent, okay? And this is one thing that the deep learning told us, is that don't be afraid. If you have something crazy to optimize, just do gradient descent, right? So let's do gradient descent. Now this becomes an exercise, right? If you're just a calculus, if you're good at a calculus, you can do this in one night, okay? I'm pretty sure. Do this, derive what this looks like. Then if you sort out what the gradient looks like, it has an architecture like this, right? This is the previous z, right? Every gradient from the previous iterate and goes through several operators. They're corresponding to the expansion term, the compression term, denoise, and aggregate them, do a software shielding, and projection. And of course, it's doing the optimization, right? There's identity, hence the skip connection, right? What this looks like. This is the architecture of the gradient of this object function, right? It looks like a residual network. This looks like a mixture of experts, right? Naturally shows up this way, right? This is actually what we called several years ago, we called this ReduNet. It actually can derive the neural networks architecture of ResNet and ResNext and a mixture of expert in this way. At least the meta structure looks exactly the same. And it actually works. And also, if you want to impose the object is environment, translational environment, those operators automatically become convolution. You derive the convolution. You don't impose convolution. Okay, convolution comes from enforcing that this object function is invariant to translation. This gradient naturally becomes convolution on the domain, right? Then what about the landscape of the object function? Is it easy to optimize? It turns out it's actually very easy, right? The global maximizer of this object function precisely corresponding to subspaces orthogonal to each other, right? And also, well, you say I'm not that lucky, right? Sometimes I get converged to a local minima, local maxima. And it turns out even the local maxima has exactly the same configuration. Only that the subspace may be missing, a couple are missing, okay? Merged together. That's it. So if you maximize information gain towards pushing things to the piecewise Gaussian, you always get this kind of piecewise linear Gaussian representations. Is this all? Probably not. This only gets the internal representation well, but very often, right? If my brain sees apple here, I only want one neuron to fire, okay? Here it still has two coordinates, right? So if I want my representation to be sparse, only one neuron to fire, I want each subspace to align with my axis, with the physical basis I built to remember this thing, right? So you wanted this to be a little bit sparse, just rotate it so that the basis gets lined up, right? So you add to the compression. You can think about the first two terms are intrinsic, but this one is a little bit extrinsic. This one promoting by coordinates z, the firing are sparse, right? Remember these days that Strawbeck spent a lot of money trying to say the neural networks learned are sparse, right? This is actually trying to do. Our brain is trying to sparse representation, right? To make this is organized. Oh, now then you have to just deal with a slightly more complicated object function, right? There's one more term. Then how do we compute the gradient? Let's do that again, right? Well, there's gazillions ways to how to do the gradient descent. Let's just choose a sort of a natural way, okay? We'll show better ways later. Right? So, for example, there's a compression term, there's a sort of expansion, and this is a sparsity term. Let's group them together, do one, do another one. Then we do alternating minimization, right? Fix one, minimize another one, right? This is the standard operation optimization, right? So compression becomes this, and then you do specification and rearrange. Then let's look a little bit closer what the operator looks like. The compression term looks like this. You spell them out, they're exactly like the attention heads. And in fact, it's just simpler. The K, V, U are share the same linear projection. You don't need the three parameters. You don't need the three submatrix. You only need the one, okay? It will do the denoising for you, all right? The second one, sparsification becomes this operator, right? We call this is standard. It's called ISTA, right? Sparsification, and become this, right? So here, this architecture is exactly doing the optimization for you, computing the gradient, maximize the gradient descent, right? Maximize the rate distortion. And suddenly you build this, keep in mind, remember we're doing one iterations, right? Optimization. We keep the iterate, we compute the gradient, right? They stack them together, right? Keep k iterations. The solution gets better. So then you actually can think about it. Then you actually end up with the deep networks, right? And this deep networks is completely explainable, right? Because every layer is based on the subspace, based on the code, sparse code you learned, try to do denoising, okay? And do that again and again until you get the piecewise linear structure. And of course, we don't know the code book. How do you learn that? Backpropagate. We'll find better ways to do that later. We'll talk about it later, right? The backpropagation allows you to learn the code book. The forward is based on what you learn, you apply to your data, to denoise, to compress, and to sort it out. And now you actually end up with, see, the black box becomes something completely open, right? I can replace this with something completely transparent. Every operator is derived from the common object function, which is actually objective. It's not subjective, right? It's the measure volume, the code book. And does this work? Actually works well. It's even better, right? So turns out that not only that this is much simpler than this is much more explainable than that. And it turns out if you train the neural networks, the VIT, compared to VIT, right? This actually, each attention will precisely group what's similar, separate what's dissimilar. Legs, body, head, ears gets grouped separately. So basically, each layer learns statistically, geometrically meaningful structures, right? So the network is fully mathematically explainable. Even you can argue the structure learned becomes statistically meaningful, right? So I know there's still a lot of people these days try different ways to empirically design neural networks. Mamba, samba, I don't know, different dance around. Try this, try that. Since 2023, at least my group will never do anything empirical, okay? Everything's designed from first principle, right? How to make things more scalable? How to get rid of anything's redundant, unnecessary? If I don't care about sparsity, can get rid of the MLP layer? Yes, you could, right? You end up with simpler attention-only network. Or everybody complain, right? Attention is quadratic. Because we have 300 years of gradient descent, algorithm, optimization, use the trick. So you just replace the object function. We know what we're optimizing, right? Replace the object function with a variational form. You end up with an operator that is actually linear complexity. This is derived from first principle, not tried, okay? Oh, wrong RWVK. I don't even remember those networks, right? Let's try Mamba, Samba. I mean, that works somehow. But this is actually can derive, okay? And you can explain everything here. And it actually gather token statistics. You can even know exactly statistically what this operator is doing, okay? Why you reduce the complexity. Right? And just give you a flavor of this, right? So again, everybody these days talk about a world model, visual model, right? Meta has a big team, right? Under FAIR and so on. Let's train using unsupervised learning, do a Dino. They have like 100 people. Did this 3-4 years, right? This is Dino 1. Now everybody world model is pre-trained with this, right? RAE, everything pre-trained this. Dino 2 gets a little bit more complicated. This is actually work done by 2 students at Berkeley, all right? And since you know exactly what you're doing, try to learn interpretation, and you can derive much simpler, right? Simplified Dino, version 1, version 2. And not only the network is dramatically simplified, and actually performance gets better, okay? And also you can see, this is comparing with all the hyperparameters, right? The systems for that network. They're completely gone. You have a much, much simpler, get a better performance. Right? This just gives you a little bit of idea about, right? Before, we always try to say, oh, let's design neural networks, right? Fit the input of the data better, right? And after you learn, you train billions of dollars, right? I mean, you still you call the space you learn is latent, hidden, right? I believe this is the reason why Elon Musk fired all the XAI co-founders, okay? If I spend $10 billion and you tell me what you learned is hidden, you don't know what you learned, right? That's the reason why there are so many prompt engineers, guys, okay? Why everybody is writing skills so that they can say, let the network churn out things they wanted, okay? They create new jobs, great for them. And now it's different, right? So now we know the network is trying to achieve the means to the end, try to organize the information, right? And also, the deep network is trying to precisely, iterative way to do the optimization, and the subspace and dictionaries. And you learn, after you train, you know what the geometric structure you're learning, right? Okay, I'll just try to be quick, a few slides. And so, now is this all? No, of course not, right? So through compression, you will lose things. You don't know if the solution you end up with is sufficient, right? How do you make sure that if the optimization is incremental, greedy, how do you know your solution memory is complete? The only way to check it is decode, to predict, right? You decode to use it, to predict what happened in the real world, right? And this is exactly autoencoding. This is exactly the problem Hinton works on and won him a Nobel Prize, right? And for us, now we know encoding, decoding. Encoding is linearizing, denoising, compression. And the decoding is exactly the inverse process, right? Now we know the architecture is a white box. You know exactly what they're doing. You remove something, you add them back. Okay? The only thing you have to change, this has become an exercise for us now. You can design autoencoding completely as exercises, right? Unlike Kai-Ming did this, he has 1,000 GPUs, right? 10,000 GPUs, right? God knows how many ways, how many things he tried to get this mass autoencoding to work, right? Even the network is asymmetric, right? No, this is pure exercise, okay, right now. And the performance is the same, even better. And now, think about it. If we know the distribution we learn is low dimensional, and we try to recover, to do a conditional recover, right? We see part of the image. What is the common problem everybody is solving these days? I observe part of the samples, some pixel I observe, right? So we should restrict the solution into some low-dimensional structure in the image spaces. And also, again, the distribution of lateral image give another curve, but not in analytical form. How do we solve this constraint optimization? Everybody's doing the same. Solve constraint optimization. Even I know this constraint, how do you enforce numerically compute? Continuation. Start with random and gradually continue, right? That's exactly Lagrange multiplier is trying to do, right? Augmented Lagrange multiplier. Heavy ball is all doing this. And except here, this is not analytical, but you know the denoising process. You enforce that. So denoising, continuation are exactly doing the same thing, okay? Just under different names. So yeah, just a very few minutes, I'll just summarize. So the right mental picture is that you want to learn the distribution and learn a good representation, then access to it. Is this everything? Probably not, right? So nature does not have this option. You cannot measure x and x hat, okay? You don't know the 3D ground truth. Nature can do has to do everything internally. Nature does this in a precisely, only in the lattice space. Close the loop. Right? This is the answer that already Nobel winner gave us about 80 years ago, but now it's completely forgotten. Everybody's end-to-end, okay? Let's everybody have billions of dollars, big models, scaling up, right? We're done, right? We're marching to, and does deep network works? Yes, closed loop works, right? Only thing you have to term is that use the rate distortion as a reward. Play a minimax game to explore and check if your prediction is right or wrong. That's the only thing you have to do. You can learn everything completely unsupervised. This is work with Yang Kun and his student. And so you can see those block structure shows up. I mean, the contrast is bad, right? And that's exactly nature learned, okay? This is the memory from monkeys. Nature learned how to sort out objects in a precisely block diagonal way. Different categories of objects sort out in our IT course in a very, very similar way. And they learn this in a predictive closed loop fashion. Right? And this is work with Doris Chow. We're trying to, during the pandemic, we had nothing better to do. Just wrote something. And also, actually, 2022, incidentally, Hinton admit nature does not do back propagation. Okay? Nature learns in a closed loop fashion. All right? It doesn't have that option. Hence, for many years, we're doing this, where I try to do open-ended model are for a closed world, however large. Closed loop system are for open world, however small, right? And that's the way to learn, right? All nature, all intelligent systems are closed loop system, no open ones. And don't say deep networks is optimizing complexity. That's kind of embarrassing. I mean, if you say that, you don't even pass undergraduate CS degree, okay? This is not computable. And even you are able to compute it, you get a random code. Is your memory like Bitcoin, right? The random digits? No, it's highly organized, right? It's computable. And also it's not even, it has to be scalable. That's why DNA and BP are popular. By the way, nature doesn't have this option. It doesn't have $1 billion, right? Doesn't have gigawatts. I only have 18 watts, right? So has to do something extremely more efficient. So what would be the architecture? This is a picture I drew with Yana Kuhn and Doris when we wrote a Murray proposal about 7 years ago, right? So we believe that all the things are really doing this highly parallel, right? Autoencoding. And all the 5 senses, modality, their structure gets highly structured, then develop language on top. Right? Language is not a modality. By the way, that's very embarrassing. Say language is lossy code we learn to interpolating our physical world model. Okay? And now let's try to attempt to give a little bit definition what is intelligence, summarize. Right? Intelligent system is the one that has the mechanism to self-correcting and self-improving existing knowledge. We are confusing 2 basic notions, knowledge and intelligence. Knowledge is the product of intelligence. Okay? Like you're confusing Apple with iPhone, okay? They're 2 different things, all right? So knowledge is actually our derivative. The efficiency to learn knowledge measures how good your intelligence is. GPT does not have intelligence. It just have knowledge, static knowledge. Child has intelligence, but not knowledge yet. So now you relook at the history, right? The whole life is actually precisely improving the efficiency of the intelligence. Right? The code book is slightly different. The information encoded are slightly different. The optimization mechanism are different. Nevertheless, they share the same characteristic about learning has the ability to learn something unknown from the world, okay? For the observations and the iterative. And the efficiency, intelligence, the derivative gets larger and larger, okay? And now, this is some even more embarrassing stuff, right? Everybody say we are artificial intelligence, but this artificial intelligence is really not that artificial intelligence, right? Anyone even bother to read the 1956 proposal? Anyone? Yeah, so except old-timers like us, right? And if you see what they're trying to do, you can compare, today we're doing denoising, compression, object recognition, right? Compared to the 1940s, what the people are really trying to advocating, right? Signal processing, information representation, game theory, algorithm control, reinforced learning. We haven't got this point yet, guys, right? We're using inductive method to emulating deductive inferences, okay? So this is actually very, very kind of, everybody talk about the Turing test. Anybody bother to read the 1950 Turing's paper? Yeah, see, only old timers, Jesus, right? Guys, today when you go out, it will be embarrassing for you to say, I'm interested in artificial intelligence. Okay, you don't. Your knowledge about intelligence, artificial intelligence comes from Wikipedia, okay? Right, I mean, Turing wrote the paper. Turing doesn't give an answer to Turing test. He actually, the whole paper is trying to, can we define the question? Can machine think? What do you mean by that? Okay? And can you test? Today we can make this more accurate, right? Can we have a method to check if the system is doing things inductively or deductively? Or even before that, maybe a system can really learn on its own, right? That's what the Yang Kuhn talks about. Why big model does not even have the level of intelligence as animals, okay? Because they cannot self-learn. And also, scientific proper test can really machine has the kind of capability as scientists. What's the difference between hallucination and hypothesis? It's about consciousness, right? If I hallucinate, I don't know I'm wrong or right? I believe it's right. But when you hypothesize, you know there's a chance you're wrong. That's why you have to verify it, right? You have to prove it. So finally, I just wanted to give us a little bit say, right? So I think it's time. Intelligence can be a scientific subject, just like physics. We find its scientific principle, phenomena, and also exercise and the mathematical theory, right? And ask some basic questions. And if you forget anything, this is a quote that Einstein says about science, right? Make everything as simple as possible. The first sentence is about the parsimony. The second sentence, but a lot of any simpler, consistency, right? That's exact. Science and intelligence are doing exactly the same thing. Exactly slightly different, right? So I would encourage students, these days, every student, young people said, oh, I cannot do artificial intelligence unless working in a big industrial company, right? No, absolutely wrong. This is a golden age, right? I think it barely started. We barely scratched the surface about intelligence, for God's sake, right? And now there has been a lot of practice, has been a lot of phenomena, but really begs to be explained in a very systematic, rigorous, and fundamental way, all right? I think this is a golden age to really be able to develop a theory to explain what intelligence is and be able to implement it. And today's overview, and if you're interested in the really theoretical evidence, the rigorous chain of theoretical evidence, and also experimental evidence, right? You cannot take my words for it if you don't. Go to read the book. There's a very, very systematic, organized, all the many years of work, right? It's a complete open source book, right? Give you very, very systematic chain of theoretical evidence and experimental evidence, right? And this is truly actually a team effort, right? Many people at Berkeley and Chicago and New York, Hong Kong, Johns Hopkins, Michigan, and UIUC UPenn, all part of this effort, right? In the past 5 or 7 years of journey, right? Pursue the nature of intelligence, and that's actually the journey, right? Thanks. Sorry, taking a little long time.
Time for questions, but if people need to leave, they can leave now.
Yeah.
So with that,
So,
and ones who want to stay for a question, I think
so I talk about the principle. There's no time to talk about how this actually really works for a real world problem, right? And you can think about this principle applied to visual data. How would we change visual, right? Our visual model is just application of it, right? The ability to acquire visual memory, right? Then what measure memory, what structure of measure memory allows you to do, right? Recognize, right? So I've been working on 3D reconstruction for many, many years, but these days everybody doing regeneration. But turns out our visual memory is precisely a combination of, it should be generation-based reconstruction, right? You actually can apply this new principle to visual memory, you get much, much better results, right? So I just wanted to show you, some of the recent work that you actually can recover, combining really generation, right, to reconstruction. Anyone, you can ask questions. I'll show you this, what you can do, right? From a few examples, you really can reconstruct the understand things just like our visual memory, right? Take a few images, you actually can not only get a 3D reconstruction, you can understand each object, and also their egocentric, object-centric, allocentric representation. All the geometry can be inferred. Completely, the understanding of things is based on the visual memory model you have. No longer just get a whole bunch of point clouds, right? You actually can get the parts you don't invisible, you generate. The parts visible, you reconstruct, right? Just like our brain is doing, right? So you can do a lot of interesting things now. Allows you to really manipulate understanding the world the way our visual memory is doing, right? Allow us to imagine, inference in an egocentric, allocentric, object-centric way, right? And no longer just do reconstruction for the sake of reconstruction, or generation for the sake of regeneration, right? Our brain is actually merged, right? So this is sort of a journey. I started 30 years ago, took Jitendra's course, studied 3D reconstruction. It took about 30 years to really at least have a hope to truly build a visual model emulating the kind of mechanism that we do with our visual memory, right? Generation-based 3D reconstruction that truly capture the complete representation that allows us to do spatial reasoning, inference, and prediction, right? So yeah, just give you a little bit idea, right? Indeed, without really understand the principles better, we will probably still stuck with some local minima and try to make a reconstruction better or make generation better, right? And now you actually can truly integrate those in a very seamless optimization framework, right? No hack, right? Oh, there's some engineering, but, right? Good. That's all. Thank you. Good. I can stay a few minutes if you want to chat with some individual meeting questions.
Yeah. I know you were saying that, why don't you use the... Hello, hi. Can you hear me now? Can you hear me?
Yeah.
So I know you were talking about the fact that since there is translation invariance, convolution comes out of it.
Yeah.
Could you talk a little bit more about that? What do you mean by translation invariance width? You mean position?
Very simple, great question. So I didn't get a chance to talk about it, but see, in our case, see, in our brain, right, we have an object, right? If I translate it, it's the same object, right? Doesn't matter where it is. So from a compression point of view, if I translate, this is a different image, right? This is a different point in the space now, right? In the visual space, image space. Now, if I treat this whole set, all possible translated objects as one set, I compress them together. Treat as one set, compress them together. Don't treat them as separate image. Then that operator, the operator to converge, to denoise against such a structure, that operator automatically is a convolution. I was actually amazed by that because this is the first time actually we derive convolution from first principle. Not only that, turns out, guess what? Those convolutions are not arbitrary convolution. It turns out that the way to compute them, there's in the frequency domain, computing those convolution network is much, much more efficient than the time domain. I don't know if there's a correlation, our brain computing in the frequency domain, okay? So there's actually very interesting mathematical evidence that for that particular operators, the convolution operators, computing in the frequency domain, the complexity reduced from quadratic to linear. It's actually quite amazing, right? So as a control person, right, we always taught, right, frequency domain, time domain, kind of equivalent, right, just your preference. But turns out in nature, for that kind of compression operator, denoising operator against translational invariance, that kind of operator has very special structure. The computing in the frequency domain, you convert everything in frequency domain, you gain tremendously in computation. Very interesting. Yeah, that's actually in the paper, in our paper. Yeah, it's actually in the paper, in the ReduNet paper. Yeah.
Thank you, Professor. That's a great lecture. I got a question. So in your lecture, you talk about like the importance of open the black box to be a white box. But like, why cannot we just like use reinforcement learning to, for example, like for us human, we don't need to know the quadratic equation and the Newton's law to play basketball.
Yeah.
So why don't we? Why do we need like to open the black box? Can't we just like using the reinforcement learning? What are the key things do you think for us to march to the next AI genre?
Great question. I mean, in fact, yes, you know, just like as I said, many of the networks, right, you can still try and error, right? You can do reinforce. It's still the structure will pop up. If those operators, layer-wise, the operators are universal enough, they can approximate anything, almost many things, right? But again, it's a winning ticket. That's why it's called a lottery ticket, right? You know, learn something. In fact, the VIT learns something, but if you visualize it, it's a mess. You don't know. Unlike the white box, you see those legs, body, emerge. At least statistically, geometrically, the structure learned is transparent to you. Otherwise, it's hidden there. It's still in that big space. It's latent, hidden, right? Then you do, in Chinese, we call 亡羊补牢, right? All the conditional. That's why everybody doing conditional neural networks, right? Control net. Everybody become prompt engineer after training the big models. You don't know where is what. You don't know what to learn there. Yes, nature doesn't care. We don't care as long as we achieve those purposes. But the nature do care in a long time access. Through natural selections, the ones with the more energy, using more redundant network, gets wiped out, right? The ones eat 5 meals a day compared to the 3 meals a day, the advantage shows up. Okay? So there's a natural selection will make things more. I'm not arguing even our brain is optimal, but it's selected. It's better than before. That is a different time scale of optimization, right? Different mechanism. Again, it's trying to get things better, getting things more structured, getting things more organized, right? We may not have reached the end of it, but we're pretty good, right? Our cortex is already very, very different from the modern big networks, which takes gigawatts. People are even talking about, multi-gigawatts, right? To train neural networks, right? And again, so have a structural representation is highly, highly important, right? Compression is not the all story, right? You don't want to compress to the wazoo, okay? If you compress to that, you get the individual points. You memorize every individual point. Or you compress data to the wazoo, you get the random bits, okay? And our memory needs to be accessed, used repeatedly. So the structure we have to access something in fraction of seconds, right? You don't have time to write the right prompt so that the outcome will be what you needed, okay? Or everybody share the skills these days, right? To play with agents, right? It's just driving me crazy. It's all post hoc fix about something you don't know. Yes, it's useful, but you don't know where it is, right? So if we want to duplicate the intelligence, we better know what we're doing, right? Make the architecture parsimonious and meaningful, and also make the learned memory structured, meaningful, right? So you have used much, much more efficiently. You don't have to control, right? I mean, you look at what the past few years, right? It's a great way to produce papers, right? Producing influential papers. You don't do it quite right. Everybody's trying to patch fix it, right? Control this, control that, and how many control nets papers written to try to make the diffusion model better, right? And how many papers make the prompt engineers better, right? 10,000, right? It's all entropy, right? The entropy is too high. So academia should be the denoiser. We should not be the industry. So I always say, right, the industry makes things better. Academia should make things right. Maybe not the right solution, but the right direction, right? Ask the right question, point it to the right direction, then we iterate from there. Unlike these days, we find something, we just engineer to death. That's probably needs to be re-examined, that kind of practice. It will improve, right? You can always make things better, faster, bigger scale, and the benchmark higher. But it's come same old practice, right?
That's inspiring. Thank you so much.
Sure, thanks.
I'm being told that 5:30 is official.
Okay,
at the end, so
okay, thank you.
Thank you. Thank you.
All right, thanks. Yeah, it's just a little bit over.